Before we dive into learning Lagrangian and Hamiltonian mechanics, there is something important you should know. No scientific theory is perfect. Each one shines brilliantly, but only within its own limits. Newton wasn't wrong. His framework just cannot handle everything. That is where Lagrangian comes in, and even where he steps aside for Hamilton. So let us take a quick journey through why these powerful ideas exist in the first place. They say great ideas fall from the sky. Well, for Isaac Newton, one supposedly did. An apple dropping straight to the ground, from this quiet moment emerged a profound idea. That every motion in the universe, from a falling apple to the sweeping of planets overhead, the path of a projectile to the movement of celestial bodies, force equals mass times acceleration. Once you know the forces, you can actually predict exactly how something will move. So F equals to ma unified motion under a single principle. For the first time in history, motion became calculable. Newton's laws turned physical problems to be expressed as equation. It turned physics into mathematics. This opened a door to calculus-based physics. It laid the foundation of engineering and technology and a lot more other things. But however, Newton's laws encountered certain problems. I won't say problems, but certain limitations. Now, when we consider using F equals to ma in many systems where there are a lot of constraints, a lot of things which are happening as variables, F gets complicated. That means it is a complicated combination of gravity, tension, normal forces, and various other things. Think of this machine which has got a F. We need to calculate this one, the second this one, and a third this one. Now, if we consider, for example, a kind of a pendulum. So in order to write Newton's notation, you must resolve gravity into components and also deals with tension of the force that is lying in the string. So what we get from here is that number one, we need to find out what is called the radial direction, which is pointing towards the pivot, and we get a kind of equation like this. Then we have to consider what is called the tangential direction, which is perpendicular to the string. So eventually what you can see, just as the first topmost illustration shows that we have to divide force into various components, here also we have to consider various components when we used to describe a single pendulum using Newton's equations. Now, to find a force, we break them into a couple of components. For example, you get a kind of a two-coupled equation. After that, we get acceleration, where there is a theta double dot and a theta dot square, which appears in different places, and the gravity components involve sine theta and cos theta. That means we can say that in order to just simply define this single pendulum, we must find all forces, decompose them, write separate equations, eliminate the constraints, and then we need to solve. Now, problem exists more when we move from a single pendulum to what is called a double pendulum. Now, here you see a double pendulum. It is just a pendulum attached to the end of another pendulum. So it looks simple, two rods swinging freely, but its motion is extremely complex. So when the top of the pendulum moves, it affects the bottom one, and when the bottom pendulum moves, it affects the top one. Both motions influence each other at every moment. Now, how will we use Newtonian mechanics using F equals to ma? This is where the limitations come. So what Newtonian mechanics basically has to do. So you see that with a single pendulum we encountered certain steps, but with a double pendulum, first we need to find out or write the force on mass 1, that on mass 2, include the tension on rod 1 and rod 2, resolve all the forces into certain components, write separate radial and tangential equations, include gravity for both, and we get something which is called a four-coupled nonlinear equations. For example, for the mass, top of the mass which the bob is suspended, we get an equation like this. For the bottom mass, we get something like this. Now, as you understand, as we move more towards the complexity in terms of dynamics, Newtonian mechanics or Newton's equation faces this kind of I would say complex and detailed and heavy calculation. So the question rises how to make things simple and clearer. Is there a cleaner or a simple way to describe motion without chasing those components or forces where there is a force on mass 1, mass 2, tensions, etc. And this is exactly where Lagrangian mechanics come in. So in the next part of the video, we need to understand, and we are going to understand in simple language, what is Lagrangian mechanics. Now, in general, we say that from Isaac Newton, when we move to Joseph Louis Lagrange, 736 to 1813, so we can say that Lagrange actually did not replace or erase anything out of Newton's equation. He just generalized them. And generalizing gave us a language that works not only for simple system, but for the entire world of modern physics, and I can tell you even beyond physics. So the Lagrangian actually do not deal with force but with energy, and the typical equation looks like this. This is basically called the Lagrangian, a mathematical quantity. T is the kinetic energy and V is the potential energy. So if we want to tell in simple language what does this equation means, we can say that the Lagrangian, which is a mathematical quantity, is the amount of motion energy of an object T minus the amount of stored or restricting energy it has due to its position, which is V, which is called the potential energy. Now remember one thing which is very important, that this L is not a physical quantity. That means it is a mathematical quantity and it doesn't represent anything measurable like force or energy or something. Instead, it is just a tool and it is used to calculate how a system evolves over time. Now, I understand this looks like a kind of a superficial definition, that how it is a tool and how it is not a mathematical quantity. I would request you to look at this video of mine, What is Lagrangian, in my series of BSc, which is called Bit-Sized Concepts, and further in this video, which is called the Euler-Lagrange equation, which will give you a detailed idea, understanding of what do we mean by it is a mathematical quantity and not a physical quantity, and so on. Now, if we now consider and revisit the mass of the pendulum problem, the single pendulum problem, we know there is a radial and tangential direction and other things which we have already mentioned. Now, if we use the Lagrangian method in order to solve this single pendulum problem, then we already know that we have a kinetic energy, which is half mv squared. Then we can calculate the potential energy, which is there. And using the Lagrangian simple equation, L equals to T minus V, kinetic minus potential, we get something like this. You can check on the equations later. But what is important is that we need to apply the Euler-Lagrange equations and we get easily to this. So what actually it tells is, you can see the Newton's equation, which is quite a bit complicated and quite a number of coupled equations that we have to use in order to solve the single pendulum motion, whereas in Lagrangian, we can quickly calculate this. That means that Newtonian mechanics, where it has got its limitations, Lagrangian mechanics is taking it up. It is not using force, because for each force we have to calculate many complex equations, many parameters. Instead, we are taking as energies. Hence, energies actually helps to solve the problem much easier instead of considering forces and their constraints. And there is a wonderful story, a very inspiring and important story of how Euler and Lagrange collaborated, and what we call the Euler-Lagrange equation has come in play. You can go to my channel Physics for Students and go to the short section and can hear it down, watch this story, the story of Euler and Lagrange, and I'm sure you're going to enjoy this. Now, if we now revisit the double pendulum problem, which we were trying to solve through Newton's equation, so what we get is that we see there is a mass on number 1 on the top pendulum, the tangential direction, and mass 2, which has also got a radial and tangential direction. And this double pendulum actually shows Newton's limitation, and it explodes into a kind of a four tangled force equations, which is quite difficult to solve. Now, let us use the Lagrangian method to solve this double pendulum problem. Here you can see we will plug in the Euler-Lagrange equation. We will get one equation for theta 1, one equation for theta 2, and then this pair of coupled nonlinear differential equation describes the complete dynamics of the double pendulum. So, I'm not going to explain the derivation etc., which you can look up in any classical mechanics book, but what is important is that here you can see there are no force components, no tension, no trigonometry that you need to solve, and there are no separate radial and tangential equations, which was there a few seconds back, which I showed you in Newtonian mechanics. So what it shows actually is that they come directly from Lagrange's equation. Also they contain only the physical variable, which is the equation on the top, theta 1 and theta 2, and they represent the true equations of motion. So up till now what we have understood that instead of considering force, if we consider energies, then all the messy trigonometric and four coupled equations actually reduces to this, and we can quickly and easily and very effectively find out the motion of the single and the double pendulum considering the Lagrangian method. Now we have understood the the pitfalls or the limitations of Newton's equation, but there are further problems even in terms of Lagrangian mechanics, which led to the formation of the Hamiltonian equations. We will come to that part later. But what I'm going to explain and what is pretty important in this is that up till now we are talking all about the motion in a very traditional way. That means we have a position, we have a velocity, we have an acceleration, and Newton describes everything using position and acceleration. But as science progresses, as physics progresses, what we have found is that knowing just the position of a particle is not enough to describe its state. By its state means everything that you want to know about the system's configuration, the movement, where it goes, where it evolves, and everything. Now, what we found as science progress is that we need to also find out what is called a momentum. So that means only the position x is not sufficient, and we need to find a pair which is called xp, and this xp in technical term is called the phase space. Now it will take another video to explain phase space, but to tell you in a very simple language, you can understand phase space is a way of describing every single thing that you need to know about a system at a given moment by listing all the things you need to know to predict where it will go next. That means you can imagine you want to describe a moving object. Knowing only where it is not enough. You also need to know how fast it is moving and in which direction. So phase space is a kind of a map. So a system's evolution in classical mechanics can be viewed as something as a trajectory. So I need to know, or you need to know, QP. That means at one instant, how can you uniquely determine the future and past evolution of the system if you know the present? So what we can tell is that the concept of phase space is basically what physics need was a formulation where position and momentum appear on equal footing. The equations are first order, which will make things easier, and the flow through phase space is visible. Now Newton's framework, as you have seen rightly here, I have mentioned that it is entirely in configuration space. That means it is not on phase space. And x double dot actually only gives you the position. No equation for P, no equation for how momentum changes directly. So we can say from here that Newton's framework lives entirely in space configuration, position, not in phase space. Lagrangian mechanics, as we will see, is better, but it still produces second order differentials, which are, I would say, and it treats velocity as the main variable, not the momentum. So there are problems, there are limitations, because Lagrangian mechanics does not fit well with phase space. In simple language, you can understand phase space is something which is also taking in momentum. It is a way of describing everything about a system state at a given moment by listing all the things that you need to know to predict what it will do or how the system is going to behave next. And as you can see, it only gives position for Newtonian framework. We need position and momentum taken together as a pair. So here you can see Newtonian mechanics can be difficult for these kind of systems where we are trying to describe action angles, variables, stable orbits, chaotic system, quantum mechanics, which is fundamentally very much energy based, and statistical mechanics, which at its core use things like partition function, entropy, and these are all what we call is energy based. So Lagrangian mechanics is good, but still uses a second order differential equation. But second order differentials are harder to answer or harder to analyze when we are dealing with stability, chaotic behavior, numeric simulation, multi-body systems, phase space flows, and so on. And remember that this one q double dot t, in simple language we call it as the acceleration of q with respect to time. So the Euler-Lagrange equation is always second order. Q double dot T always appear. That means this Euler-Lagrange equation won't give us anything regarding natural phase space, no symmetric rule, hard to analyze the structure of motion, and no ideal for numerical or chaotic system. So that is one of the limitations of Lagrangian mechanics. Now also the second point or the limitation is that Lagrangian mechanics does not smoothly apply in quantum mechanics. Now why it is so? Now the reason is that the Lagrangian deals with an action principle, which we know is this one, and classical notion comes from the stationary action where delta S equals to 0. And this produces the Euler-Lagrange equation. But on the other hand, the quantum mechanics, the heart or the pivotal equation of quantum mechanics is Schrödinger equation. And Schrödinger equation, as you see here, this H is using Hamiltonian. So from here we come to the next part of our video where we are trying to understand the limitations of Lagrangian mechanics and how it does not fit in and how quantum mechanics fits with Hamiltonian. So if I take the ordinary general Schrödinger equation, what it tells basically there is no Lagrangian, no stationary action principle, there is no T minus V, and there is no Euler-Lagrange equation. In quantum mechanics, as you have know, that this momentum becomes an operator, and in case of a free particle, the solution looks like this, and there is absolutely no direct way to obtain this operator from the Lagrangian. That means what we can get is basically a classical momentum, P equals to mv or q dot. But it actually does not tell how to quantize it. And as quantum mechanics, the name itself suggests that it needs to be quantized. So from here what we can say is that the Lagrangian gives you obviously a classical momentum, but it does not tell you how to turn that momentum into a quantum operator. And quantum operators are required because in quantum mechanics, momentum basically becomes not as a variable but as an operator. And this is the magic which Hamiltonian does. So the limitation we have understood for Lagrangian mechanics, not fitting it with quantum mechanics, the need for an operator, and hence we need the Hamiltonian. So Hamilton's energy-based frameworks actually maps directly into what is called quantum mechanics. I won't be describing in details right now. So classical Hamilton's equation and quantum Schrödinger equation both have an Hamiltonian, as you can see here. And the Lagrangian L does not appear anywhere in the standard Schrödinger equation. The second thing is what is called Hamilton's phase space structure actually becomes commutation in quantum mechanics. This is basically called the Poisson bracket. Don't worry, I will come to this part later. But let us understand that in classical physics, this one which you can see right on the screen, there is a rule called a Poisson bracket that tells you two quantities in phase space like position q and momentum p, how they relate to each other. So when we say in classical physics q comma p equals to 1. Now, when we move to quantum mechanics, the classical rules turns into a rule about how the operators for position and momentum fail to commute. That is what it is telling. QP is equals to IH. So this replacement, actually turning Poisson brackets into commutators, is one of the foundation of quantum mechanics, and that is why we call it is the birthplace of quantum mechanics. And the Lagrangian has no natural bracket structure. So what we can tell from here that this replacement, turning Poisson brackets into commutators, is the foundation of quantum mechanics. It tells us that quantum quantities do not behave like ordinary numbers. The order in which you multiply actually matters. That means 2 multiplied by 3 is not equal to 3 multiplied by 2. And this is the basic definition of commutation as you have learned in quantum mechanics. However, we can understand that Hamilton's energy-based framework maps directly and smoothly in quantum mechanics, and also the phase space become commutators in quantum mechanics using the Poisson bracket, and we find Lagrangian deals with nothing, and we have nothing which can actually compute L equals to T minus V. So from here we understood that Hamilton's energy fits in, etc. We come next to the next part of our video, which is called what is Hamiltonian mechanics. So Joseph Louis Lagrange actually advanced Newtonian's law using generalized coordinates and deriving motion from energy, and Sir William Rowan Hamilton completed this by using what is called a conjugate momenta, or creating a full space piece. So by definition, what we understand is that Hamiltonian mechanics transforms the Lagrangian picture into a new framework. That means it uses generalized coordinates which will be applicable to anything, and a conjugate momenta, that means it considers momentum also, thereby making a system much better to function. This is the Hamiltonian, and this is the motion of a system. Now the question is that what is the meaning of this partial differential equations that you see at the bottom right hand side corner of your screen? Now, as we can see that both Lagrangian and Hamiltonian deals with what is called the total energy. So the motion of a system is governed by Hamilton's equation. Now, if I take the left hand side equation, it tells something very simple. It tells that how the position changes. In simple language, we can tell that to know how fast the coordinate qi, which is a generalized coordinate, it can be 1, 2, 3, anything. To know how fast the coordinate qi changes, look at how the energy changes with respect to its momentum, which is at the denominator pi. So you can say in simple language, it tells momentum decides how positions evolve. If the momentum is large, the position changes quickly. The right hand side actually tells how the position changes. Right? So here you can see that to know how the momentum pi changes, look at how the energy respects with respect to the position. The earlier one was momentum, this one is the position. So we can say in simple language, force comes from how energy changes with position. If moving in a certain direction increases energy, momentum gets pushed back. So that means the first equation, or I would say the left hand side of the equation, tells how position evolves, and the right hand side tells how momentum evolves, and together they actually tells how the whole system moves through phase space. Now you can now again go back and revisit the definition of phase space, where both position and momentum are taken together. So from here, what we can talk when we're talking of Hamiltonian mechanics, we can say that F equals to ma leads to this. But this equation has brought problems. It only uses position, uses acceleration, no natural role of momentum, no phase space, and sometimes very difficult to very difficult to calculate for different coordinates. The Euler-Lagrange equation also has certain problems. It is still second order, depends on velocities, and still no automatic phase space, and it does not transit smoothly in quantum mechanics. Now comes the big brother, that is the Hamiltonian mechanics. It tells you that first order equation automatically creates phase space and things like that. So what we can tell that the Hamiltonian tells us that where something is and how fast it is moving, point number one. The math you need involves simpler type of equation. It naturally gives a picture of how a system behaves or evolves over time. It helps you see how energy moves or changes inside the system, and the method is very powerful because it can describe everything from a swinging pendulum to complicated systems like planetary motion. Now that we have understood the limitations of Newtonian mechanics, how Lagrange come in, the limitations of Lagrangian mechanics, how Hamilton comes in, now it is the time that we should look at the central idea of our video, that is What is the best book for learning Lagrangian and Hamiltonian mechanics? Now, the best book which I have found is Patrick Hamill's Student's Guide to Lagrangian and Hamiltonian. You can find out the customer reviews and you can see what are the reviews and the comments people have written. I found this is an amazing book. Now, it is not amazing just because it is well written, etc. But the way the book has been divided, the way the concepts are logically taken. So now I am not going to explain all the table of contents. Obviously, it will take a huge time. But some of the concepts that you should take ahead and you should learn and take it forward, because this is a wonderful way and a wonderful, I would say, logical sequence in how things are being done. So the book first starts with what is called a kinematics. It starts with a basic review of position, velocities, etc. and it sets the stage of the Newtonian world. Next, it takes you into generalized coordinates. Why? Because this is important, because you choose smart coordinates. Logically, it gives you an idea that you don't have to deal with x, y and z. These are all generalized coordinates which happens at any point of time. From generalized coordinates, we move in what is called a generalized velocity. Here, the time derivatives and the Lagrangian depends on this, and it is a stepping stone for learning the Lagrangian further. The book then explains a very important concept which is called constraints. Constraints mean what? That we all have constraints, etc. So it is a limit. It is a kind of a limit that a system can take. Say, for example, a pendulum. So a bob cannot move anywhere in space. It will always stay at a distance from the pivot. Then comes a bead sliding a wire. A bead must stay on the curve of the wire. Its motion is restricted to a line of curve. So just like a pendulum, the bob cannot move to and fro anywhere. A bead must stay on the curve and a wheel rolling without slipping. So all of this actually tells that there are certain constraints. Now the question is that why we are learning the constraints? Because they reduce the number of coordinates. As soon as you put certain constraints, the equations become simpler. So then let us describe with one coordinate, for example, theta. So this theta actually takes us to the Newtonian mechanics, where constraints make life hard, and in Lagrangian mechanics these constraints are handled beautifully. Why? Because we now have generalized velocity, generalized coordinates and so on. This is a very important part, and the book actually takes a good amount of care of this. Then comes a very important concept which is called virtual displacements. So a virtual displacement is a kind of a tiny imagined change in a system's coordinate that happens actually without any time passing. Now this is actually the equation. What it tells a simple thing. If you imagine giving the system a tiny hypothetical displacement, a kind of a small nudge, the total work done by the force must be zero. That means it is like asking, if the system were nudged slightly but still following all constraints, what direction could the system move? So this del Ri, it tells that it is tiny, it is imaginary, it does not actually occur in time, it respects all the constraints. And as you can see, this Fi dot del Ri, this is the amount of work, the force on the happening on the particle I would do if the system moved by a very, very tiny virtual displacement. And the sigma, it adds up everything. So now the question is that why this is important. Again, you might ask a question that why this is important. Now this is important because virtual displacements are the key, because they allow us to use the principle of virtual work and D'Alembertian's principle, which will later you will see leads to the derivation of the Euler-Lagrange equation. So this is important because it allows us to avoid calculating constraint forces, avoid decomposing into xy, and works directly in generalized coordinates. So virtual displacement is a very important concept, and this book actually does that. Now, the next important concept which this book deals pretty well and you should learn is what is called the holonomic and non-holonomic constraints. As you can see, this is the content of the book, and here you can see the difference between delta and D and the holonomic and non-holonomic constraints. I'm not going to go step by step with all the contents of the book, but I feel that knowing holonomic and non-holonomic constraints are important. So in general, what we can say of holonomic constraints is something like this. Holonomic constraints are actually a condition that tells that the particle is only allowed to exist at certain positions in space. That means it is a restriction. It is a restriction that can be written as a mathematical equation involving the coordinates only. For example, this can be written, that means it has got no velocities, no acceleration, just the position. That means it makes things simple. So why only coordinates matter here? Because holonomic constant tells you where the system is allowed to be. It cannot move here and there. That means it is constraining. It limits the allowed positions, not the motion. If I consider this pendulum again, then the bob must always stay on a circle. It does not say how fast the bob moves, only where it is allowed to exist. That means why this is important in Lagrangian mechanics is that because if the constraint only involves coordinates, then it becomes easy. You can solve the constraint equation. You can reduce the number of coordinates so that the system is described with fewer or generalized coordinates. So this is pretty important, and the book will teach you what is holonomic constraint. But remember that this actually means it is a restriction. And there are no velocity, no acceleration, just the position. And this will help you to learn Lagrangian better because you are not being allowed to move or take a lot of complexities. Just it tells you where the system is allowed to be. Now, when I talk of the non-holonomic constraints, it actually tells you the particle is only allowed to exist at a certain position in space. That means it usually involves velocities like this. So instead of limiting it in terms of position, it limits the motion or directions the system is allowed to take. For example, if I take a rolling wheel, a rolling wheel is basically something which relates linear velocity to angular velocity. That means this one, which you can see x dot or r theta dot, this is what the restriction. It restricts how the wheel moves. That means it will move in a specific direction. It cannot slip and move left and right. For example, you cannot make an equation as constant as x squared plus theta squared equal to constant. That means if I take a car, you know that a car cannot move sidewise. What does it mean? It means it is a non-holonomic restriction. A car must satisfy this equation. And this equation tells the car can only move in the direction it is pointing. It cannot move slidewise. In other words, you can say that its sidewise velocity must be 0. That is what the equation tells. So its motion in x and y must match the steering angle, which is the theta. So this is the direction motion rule. It does not restrict the car's position, only how to move. Now, you might say that, okay, we understand everything. Holonomic constraints are restricting positions. Non-holonomic constraints restrict motion. But if non-holonomic is something where, they cannot move sidewise or the wheel is restricted, the question is that why we are at all learning this? I mean to say it is difficult. The Lagrangian won't be able to solve the non-holonomic. So why it matters? So to answer this question is that why it matters, because even though non-holonomic constants are difficult, as I was telling, they cannot be ignored because there are a lot of real life systems which evolves in this way. For example, cars, because the no side slip wheel constraint depends on the car's motion. Bicycle, because the wheels enforce constraint that forbids sidewise motion. Wheels, they only move in certain directions. Robotic arms also imposes velocity constraint. Skates and trolleys, because their wheels or blades allow motion only along certain direction. So what you learn from here is that non-holonomic constraints are actually important. And these actually are all these cases, and you can understand these are all real life cases. So non-holonomic constraints actually teaches us where the Lagrangian mechanics has its limitations. When Lagrangian multipliers are needed, we will come to that. And this helps students to appreciate that why do we need the Hamiltonian mechanics. So non-holonomic also expresses that motion cannot be reversed. For example, a car can parallel park by moving forward or backward plus steering, but it cannot simply move sideways. It cannot move in sideways into a parking spot. But I remember when I went to the hills, I don't know, but I remembered I was going with my family in a cruise bus. And somehow I can see, I don't remember clearly, that there was a steering and the bus was moving sideways. I remember it was years back, and the bus cruise was moving sideways. That means it can actually take a kind of a sideways direction. Anyway, so from here what we can say that non-holonomic systems reveal that configuration space and motion space are not the same. So why we learn non-holonomic? Because many real physical systems, as we have seen in the examples, actually shows the real power and limits of Lagrangian mechanics. Now, here is a question to all my viewers and subscribers. Which mechanics or which equations actually solves non-holonomic constraints? If you know that, please do let me know in the comment box. And by the time you do a little bit research or put on your intelligent comments, I will move on to what are called the Lagrangian dynamics, the next part of our video. Now you might ask me a question, what is the difference between Lagrangian mechanics and dynamics? Well, it's a play of words. Mechanics is basically when we talk of the entire system as a whole. Dynamics is basically when we talk of what is happening internally. So this is the content of the book in terms of Lagrangian dynamics. Again, I'm not going to take everything as a whole, but I'm going to take just few concepts and explain you why these are important. The first one is called the principle of D'Alembert derivation of Lagrange's equation. So the D'Alembertian principle actually tells it is a modified versions of Newton's law. This is one of the easy way, but there are other ways of writing. It says that take all the forces, right, Fi, subtract all the inertial forces, and the result does no virtual work. That means it acts as a principle between Newton's F equal to ma and the Lagrangian formulation. So from Newton we move to D'Alembert, then we move to Lagrange, and finally we end up to Hamiltonian. So D'Alembert, then we go to the constraints eliminated, the generalized coordinates, and the Lagrange equations emerge. So I mean to say, if you talk of this one, the D'Alembert principle, which is right here as I can show you, it actually tells that take all the real forces on a system, subtract the inertial force, mass times acceleration, and the result does no virtual work. We can also say that real forces plus motion resistance, which means inertia, must balance out when tested against allowed tiny motions. So now the question is why it is taught in Lagrangian mechanics? Because it removes constraint forces. It turns Newton's second law into a form that works well with virtual displacements. It provides the bridge from Newton's law to Lagrangian, Euler-Lagrange equations, and a lot more. So this is what it actually, you can see it shows. So from here, so this is pretty important, the D'Alembert, learning the D'Alembert principle, because from here you will understand that it is a modified versions of Newton's law, and this will actually lead to the Lagrange equations. The book talks about the Hamilton's principle, which I'm not going to talk. You already know about this action principles and nature taking the least action path, deriving the Lagrange equations, and generalized to many coordinates. Now, the next part which I was talking, that if it takes the non-holonomic way, these things will be solved by what is called Lagrange is this one, the Lagrange multipliers, right? So what do we mean by this? Now, the constraint equation actually looks like this. What it actually tells is that this is a rule. This is a rule the system must obey. Now, it restricts how the coordinate can move using this lambda sign. For example, a bead must stay on a wire. A car must not slide sideways. So lambda is the mathematical helper that represents the force needed to enforce the constraint. It tells how strongly the constraint is pushing back on the motion. Next, we already have learned, I'm not going to explain the non-holonomic constraints and the virtual work, which is basically we have learned in the earlier part of the video. The book completes the Lagrangian dynamics and move into what is called the Hamiltonian mechanics. Here is a quick snapshot of the table of contents. Again, I'm not going to go part by part everything into Hamiltonian mechanics because it will take a long time, and that will be done further in my videos. But I would take few of the very important concepts. Number one is what is called the Legendre transformation. Now, this Legendre transformation is nothing but a mathematical way of transforming or converting the Lagrangian into Hamiltonian. So you can say, instead of describing of something using variable like velocity, it lets you to switch to another variable like momentum in a much more convenient way. So in Lagrangian mechanics, we switch from Lagrangian velocity based to Hamiltonian momentum based. The Legendre transform is a tool that performs this switch. Then comes what is called the Hamilton's canonical equations. This is the heart, which I have already explained what it actually means: the position evolution, momentum evolution, and the phase space flow. Another important concept which comes across here is what is called Poisson bracket. Now again, Poisson bracket is basically, it tells how two quantities in a mechanical system affects each other motion. That means it is again a tool. It is a tool that measures or the interaction between two variables. I will come and will give you a simple example. So Poisson bracket, understand, that tells us whether two things in a system influence each other while the system moves on. So if the bracket has got certain conditions, if it is 0, no effect. It is non-zero, they are linked. And if it is 1, they are fundamentally connected like position and momentum. Now, if I take, for example, this basic form of Poisson equation, I take out the left hand side. It is simple. It tells how A changes with position and how B changes with momentum, and then they get multiplied. If I take the right hand side out, then it takes how A changes with momentum and how B changes with position. So first was A changes with position and B changes with momentum, and the second one is A changes with momentum and B changes with position, and it again gets multiplied. What is important is this one, which I've just highlighted, this one, the minus sign. Now this minus sign is pretty important. Why? Because this subtraction actually gives you the Poisson bracket. It is very easy to show you with examples rather than going ahead and talking more about this. So if I take, for example, a position and a momentum, and I take these values, and from here we get 1 times 1, which equals to 1, and I take these values as 0, and then again I multiply and then subtract, I get this. Now I subtract 1 minus 0, which is equal to 1. Now you know from here what does this 1 actually means. It means that this Poisson bracket, if it is equal to 0, then these two variables A and B, whatever they are affecting motion. Here, if it is not 0, then they are dynamically linked. But here we come to the third point. It is 1. That means position and momentum are fundamentally linked. Now, when I talk of this fundamentally linked, this actually leads to a very important equation, this one. And what it tells, this tells that position Q double dot and momentum P single dot cannot be measured independently or cannot be known independently. They are fundamentally linked, which actually brings us to the quantum mechanics. The commutator actually tells you how much they fail to commute. The order in which you measure, as I told you, they matter. So 2 multiplied by 3 is not equals to 3 multiplied by 2. Quantum mechanics will not let you know or not let you specify both perfectly at the same time, and this is the mathematical foundation of Heisenberg's uncertainty principle. So now if I revisit the Poisson bracket, you will see that these things, this Poisson bracket thing actually comes in part of Hamiltonian mechanics. If you go to this part again, I will show you here it comes in. I'm so sorry. Yeah, the Poisson bracket. And this Poisson bracket automatically from classical physics, how beautifully you see the Legendre transformation, then you see the Hamilton's canonical equation, and then the Poisson bracket, the meaning of these brackets, and then further going here, how I take this example and this bracket, each of them tells the state of a system. So if I take QP equals to IH not equals to, which is equal to 1, or any value coming up, that means it leads to Heisenberg's uncertainty principle. So this is basically one of the very important part of Hamiltonian mechanics, and there are other things also. So let me give you at last a quick idea or opinion about this book, A Student's Guide to Lagrangian and Hamiltonian. It is a perfect for students who wants to clarify clarity, and there is no confusion if you read this book. The explanations are concept first and not the formula. The book bridges the gap between classroom physics and the real theoretical mechanics. There is a lot of examples which lucidly explains transition from Lagrangian to Hamiltonian, and the sequence, oh my god, it is wonderful. It starts from basic motion, then generalizes into coordinates, then the Lagrange, the Legendre transformation, and extension up to continuous system. So it is ideal for both physicists, and if you're an engineering student, you can read this book. So this Patrick Hamill's book is the clearest, very friendly introduction to Lagrangian and Hamiltonian, and it is perfect if you want to truly understand the subject rather than, I would say, memorizing formulas. So this brings us to the end of today's video. Apart from the entire book review, what actually I have done is that basically I have given you a complete understanding of the major concepts of Lagrangian and Hamiltonian mechanics. Thank you very much for taking up your time and watching this video. If you have liked, please do not forget to subscribe to my channel Physics for Students and click on the bell icon, because the Christmas is coming and the Santa's bell is continuously ringing, and I will also continue to ring my bell to bring you more surprises. Follow me on my Facebook handles and write to me on this email ID. Physics for Students will be soon back with a lot of more surprises and fun-loving videos on physics, mathematics and related subjects. See you soon on the next video, but till then, may the good Lord be with you.